Hello students, we're going to be studying fluids. Now the word fluid covers both gases and liquids. So water is a fluid, oil is a fluid, but air is also a fluid. And the gas, let's say, that comes out of a cook stove is also a fluid. Now for this study, we're going to need to know about various properties. And the first property of fluids that we want to look at is density. Density gets the symbol rho, the Greek letter rho. Now when I draw the letter rho, I do it like this, like that. Okay. Now density is defined to be the volume of whatever the stuff is, and the mass of whatever this stuff is, and you take the mass and divide by the volume. So density is the mass divided by the volume, so it's going to have units of kilograms per cubic meter. So as some examples, the density of water is 1,000 kilograms per cubic meter. Now actually this refers back to the metric system definition way back. You see, a cubic meter is 1,000 liters, and in the original metric system, the volume of a kilogram of water was the definition of a liter. Now the density of oil is a little bit less than water. It's 920 kilograms per cubic meter, and that explains why oil floats on top of water. And of course, air is far less dense than water. It's 1.29 kilograms per cubic meter at standard temperature. That's like room temperature and pressure. That's 1 atmosphere where we are. So let's have a quick example here. How much air is in an empty 2-liter bottle? Now I happen to have a 2-liter container here. It originally had yogurt, but it doesn't matter. The question is, how much air is in this? Right? Obviously it's 2 liters, but I want to know what's the mass of the air in there. So what we do is we're going to use our formula, rho equals m over v. Solve for the mass m, so m equals rho times v, and so the density, the rho, is 1.29 kilograms per cubic meter, and then we're multiplying by the volume, which is 2 liters, but then we need that conversion factor, and so we have 1 cubic meter equals 1,000 liters. So now we're going to have the liters cancel out, and we get our answer, 0.00258 kilograms, which converts to 2.58 grams, and a gram is really small. So that means that the air that's in here doesn't weigh nothing. It has some weight, but it's not a lot. Okay. So the next thing we're going to talk about is pressure. Pressure gets the symbol capital P. Now, I'm sorry that we have to use this same symbol because capital P got used by power. So now when you see capital P, it means something different. It doesn't mean power anymore. Now, the pressure comes from the push of billions, trillions, quadrillions of molecules that push against the wall of, let's say we're talking about the pressure behind this wall here. So we've got some gas back here, and the pressure of the gas is pushing on this wall. And that push, that pressure, is coming from the molecules hitting the wall, boink, and bouncing back like that. So they come in and they hit the wall. And so this is happening many, many times per second. Boink, boink. And so to actually, the wall, if you had a super sensitive and fast microphone like hooked up against the wall, you would hear the boom, 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 boom of these molecules hitting the wall. But it's, for something big like this, the molecules hitting the wall are it sort of washes out. There's too many per second for us to really discern it. But anyway, on a microscopic level, that's what's happening. These molecules are hitting and bouncing off the wall, and that's what gives a push to the wall. So if you think about it, it's momentum, right? The momentum of the molecules got changed, and so they gave an impulse to the wall. Anyhow, we're not really going to need to deal with that level of detail. Instead, we're just going to talk about pressure as force per unit area. And the units are going to be newtons per square meter. And then this unit here, newtons per square meter, is been redefined. We call it the Pascal, abbreviated big P, little a. Now, there are many different units for pressure because over the centuries, humans have dealt with pressure-related problems in many different contexts. And so, as a consequence, there are many different units. Here are some common ones. The bar is defined to be 100,000 pascals, which you could also write 100 kilopascals, right? K means thousands. You could also write it 10 to the fifth. Now, the word bar, B-A-R, comes from the word barometer. And the barometer is an instrument that tells you what the pressure is today. You see, when you've got bad weather coming, the air pressure just before that storm comes in is a little bit less and a little bit lower. And so, and then after the storm has gone by and good weather is coming in, the air pressure is a little bit higher. So that's what a barometer is good for, and that's where the word bar comes from. Now, the fact that 1 bar is 100,000 pascals and the average atmospheric pressure, which is called 1 atmosphere, the fact that this number, 100,000, is really close to this number here, 101,325, I think is mostly coincidence. But it's a nice coincidence. So for quick back of the envelope calculations, you can say, well, 1 atmosphere is 1 bar, and get an answer that's good to 1%. But anyway, so atmospheres is another commonly used unit, and okay. And then, another common one, especially here in the United States, where we still use imperial units, because of the British Empire, we use pounds per square inch. And 1 pound per square inch converts to 6,895 pascals. So let's have a pressure example. I have here a soda can. Well, it's not soda, it's actually a beer can. And its height happens to be 12 centimeters, 0.12 meters. And its radius happens to be 0.033 meters. And the question is, how much force does the atmosphere exert on the wall of the can? So actually, I'm just going to be calculating the force of the atmosphere on the side. I'm not going to bother with the top and the bottom. But anyway, it's still a decent example. Okay, so how much force does the atmosphere exert on the wall of the can? Okay, well, we're going to need to find the force. So multiply both sides by A, we get force equals pressure times area. Now the pressure is 101,325 pascals, right? That's where that came from here. And the area is 0.0249 square meters. And I got that by doing the circumference, going around the circumference of the can, which is 2 pi r, and multiplying that circumference by the height. And that's how I got 0.0249 square meters. So we've got these two numbers, we multiply, and we get the answer, 2,521 newtons. So that's a lot of force. That's, that's more or less the force of 250 kilograms, pushing down on the ground, which is sort of like the force of a horse, like a big old horse. Or a sumo wrestler or something. So we've got a lot of force on this. Now, at this point, I'm going to stop, and I would like you to go to YouTube. Well, you're already on YouTube, I know that. And take a look at this video. I'll put it next up on my playlist for the physics class.